Okay, so this is my first class that I'm actually teaching, and honestly, I I'm good at talking with like for scientific presentations and shit, but I'm not all that great at teaching because it's not like a thing I've done. I haven't been able to practice it. So hopefully I do well. Hopefully you guys will just be patient with me and stuff like that. All right. So what I'm gonna go over first is I'm gonna go over human evolution in the pre-upper Pleistocene, and the Pleistocene pre-upper Pleistocene was about 150,000 years ago. And the reason I'm talking about this is because extinctions aren't really new. Um, okay, so the reason I'm going to be talking about the pre-upper Pleistocene is because extinctions aren't new. And even though we're in a mass extinction right now because of biodiversity loss, habitat loss, climate change, overhunting, etc. There's been 5 other mass extinctions before this. If you guys haven't read The Ends of the World by Peter Brandon, it's actually a really good book. It's long, but the writing is interesting and you learn a lot of cool things about um, how the world and life really began, and then the kinds of stuff that has gone through just to make it to where we are right now. So I really recommend it. But the point of that is that there has been 5 mass extinctions beforehand, and one of the more minor ones actually doesn't even rank as a mass extinction happened in the upper Pleistocene, so about 150,000 years ago up to 8,000, I want to say, years ago. So the reason I'm going to be talking about the pre-upper Pleistocene and human evolution is because you have this idea of prey naivety and how that influences anti-predator behavior. I'm throwing a lot of concepts at you guys right now, so I'm going to try and explain it a little bit just in case you guys don't know. So the idea behind prey naivety is you have this predator that comes into an ecosystem, and the prey might be used to coyotes, for example. So they're used to animals that run and chase you in the open plains, open habitat. They're used to animals that are actively hunting for things, but aren't just sitting in one place. And then if you throw a bobcat into that situation, bobcats are ambush hunters. They'll sort of focus on areas where animals will come through and they're able to attack them. So if you go from just worrying about being in the same place as a coyote at the same time, as opposed to completely avoiding, for example, a riverbank because there's a bobcat there that likes to hunt there. Um, you're naive. You don't know what to expect in these situations. A lot of papers have been done about prey naivety and how that influences anti-predator behavior because um, it's a really big thing in island biology and ecology. You have new species coming in, colonizing areas because humans bring them there. So like cats, dogs, rats, etc. And you have native species that didn't evolve with these animals that are suddenly exposed to predators that act in ways that they're not used to. So naivety theory is the idea of species lacking evolutionary history with a predator, and because of that lack of history, lack of knowledge, they're easier to kill. And the reason that they are easier to kill is because they either fail to recognize that the predator is an actual predator. So maybe they'll see a bobcat, they've never seen a cat like animal before, so they're not sure how to react to that animal. A failure to respond appropriately. So if, for example, You have a tarantula that has its little nest in the ground in the rainforest, and a mouse runs across its nest and it triggers that web that lets the tarantula know that there is prey above it and it can grab it. A mouse can accidentally trigger that and maybe it'll escape. But if they don't know to completely avoid those kinds of areas, then they can get caught again. And then a failure to respond effectively when they are, in fact, faced with predator. So, white-tailed deer like to run from predators, whereas mule deer like to actually fight predators. So it's actually really interesting because when people think or when people are studying fawn survival and the differences between white-tailed deer and mule deer, they find that if white-tailed deer sort of are in mixed herds with mule deer, and the fawns are sort of mixed as well. The fact that mule deer does will actually fight predators off of their fawns actually kind of increases the survival of the white-tailed deer fawns because the predators know just to completely avoid um, these herds. So, um, in cases where white-tailed deer are just fleeing, it's possible that the fawn will be caught because it's not as fast as the moth. So it's that idea of responding effectively when in fact you are faced with a predator. And the reason I'm talking about all this is because you got humans coming in around this time, around 150,000 years ago. This is a picture of Homo erectus, and you have this animal that comes in. It's bipedal, so it's standing on two legs, not very furry, runs around in groups. Sometimes it throws sticks, and you have all these animals that are not. You have all these animals that are new in new lands that are faced with these people who are coming in because they're migrating out of Africa, and they don't know what to expect. So there's that prey naivety thing coming into play. And also, we like to run. So I'm pretty sure that a lot of you guys have heard this because it's an interesting kind of fun fact that people like to spread on the internet. But we're really special in the fact that we will just run our prey down. And I don't mean like cheetahs, like we're really super fast. Obviously, we're not. But the idea is that we will just chase and like doggedly follow prey until we just like they have a heart attack and they cannot keep on going. Um, so we're endurance hunters, and this is a completely new strategy for a lot of animals once we're leaving out of Africa. So maybe they're used to cheetahs, and they're like, okay, if I can just avoid this predator, this human, for a couple of minutes, they'll leave me alone. No, we're going to be following you for like 2 days and you're going to keep on trying to avoid us, but we're still on your trail. So obviously, that strategy of just running as fast as you can for a couple minutes isn't going to work with us. So the reason I'm bringing this in is because you have Homo erectus leaving out of Africa in about 1.9 million years ago. I'm going back like all millions of years ago because, as you'll see later, uh, what actually happens is that this area and this area, like this South Asia, Southeast Asia, these areas right here, they actually don't have as many extinctions as places like America or South America, and then Australia as well. So the fact that Homo erectus, which is kind of close to our species, they are bipedal, they were able to throw things, etc., um, kind of moved into these areas like 1.9 million years ago. We have species that are able to sort of they were already exposed to them, basically. So they were exposed to Homo erectus, they were exposed to human type predators. and they were able to sort of weather the next wave of humans coming out of Africa, which is where a lot of things went extinct. So we have Homo neanderthalis around 300,000 years ago, was in southern Europe and Western Asia. And then again, like every single time you see this pre the Upper Pleistocene, you're thinking this is an exposure event. So these predators that are in, or these prey species, or just wildlife that are in these areas are able to, are exposed to humans, exposed to human type predators in our strategies, and they're sort of able to deal with it when modern human comes out of Africa, which is in 125,000 years ago. So by 125,000 years ago, we were all throughout southern sub-Saharan Africa, modern humans, as we are now, basically. And then over the thousands of years, we just sort of spread out again, coming to South America around 13,000 years ago. So I am gonna go into climate now. So this graph on the top is from about, it goes over 1,000,000 years. So you see this decline in global temperature. And you also see this like increasing variability. So the differences between the peaks and the lows sort of increases as we go throughout the Pleistocene. And then this is also about millions of years ago, but it's actually, yeah, okay. So what we're gonna start out is like around 100,000 years ago. And what we see is that around 125,000 years ago, we sort of come out in this really, really cold point and increases in temperature. And then we start declining in temperature as well until we get the last ice age. And then we hit the Holocene around 8,000 years ago. So this idea of variability in global climate is really interesting. And we're trying to figure out what's actually happening in these times. We have glacial periods and we have interglacial periods, which is when it gets warmer and the glaciers melt, sea levels rise, etc. And people think that it's because of this thing called Milankovitch cycles. So,
need a professional website? I created one for our startup using Wix. Let me show you how I did it. First, go to wix.com.
Average temperature on Earth was 2 degrees lower. How did these temperature differences arise? First, the sun plays a role. When the sun is more active, sunspots can be seen. This can make it a little warmer on Earth, but this only involves 1/10 of a degree of heating. The current global warming can therefore not be explained by a change in the activity of the sun. Volcanoes also play an important role. During a violent eruption, a lot of ash is released into the atmosphere. This ash, if it enters the atmosphere high enough, can remain in the atmosphere for a long time and block the sunlight. For example, the eruption in 1815 of the Indonesian volcano Tambora caused the global temperature to drop sharply, and 1816 was called the year without summer. Although in the short term the volcanoes cause a temperature decrease, volcanoes cause a temperature increase in the long term. Volcanoes emit the greenhouse gas CO2, which causes the temperature to rise. The Earth was once a planet full of ice, but due to a lot of volcanic activity, a lot of CO2 was emitted and the temperature on Earth slowly increased. Milankovitch variables are a final natural influence. Milankovitch thought that the temperature on Earth was influenced by 3 variables related to the position of the Earth relative to the Sun. In short, the point is that if the Northern Hemisphere receives less energy from the Sun in the summer, the ice on the North Pole will not melt and an ice age may arise. First, the Sun does not orbit the Sun in a circle, but in an ellipse shape, in which the Sun is not centered. This is called eccentricity. The point where the Earth is closest to the Sun is annually, at the beginning of January. So, in July, the Earth is farthest from the Sun. This is summer in the Northern Hemisphere. Because of the distance, the Earth receives less energy from the Sun. The ice in the Northern Hemisphere melts less quickly. This could be the beginning of an ice age. If there is a circular shape, the Earth is closer to the Sun at the beginning of July. This gives the Northern Hemisphere more energy and the ice melts. This prevents the formation of an ice age. The eccentricity changes approximately every 100,000 years. The second is obliquity. This is the tilt of the Earth's axis relative to the Sun. The Earth's axis has a tilt of 23.5 degrees, but this changes between 22 and 24.5 degrees. The wider the angle, the more the Northern Hemisphere turns towards the Sun in summer, and the more ice melts. The smaller the angle, the less ice melts in summer, and the greater the chance of an ice age. The obliquity changes approximately every 41,000 years. The third is precession. This is a toll movement around the Earth's axis that changes every 26,000 years. Here the first two effects are amplified or limited depending on the eccentricity and obliquity. Now that you have learned how natural fluctuations in the climate arise, we can investigate the consequences of climate change for the Earth.
Okay. So, does anyone have any questions first? Feel free to drop them in the chat or just say them. If not, we can continue. Okay. So, first thing I want to mention is that I don't expect you guys to like memorize terms and stuff, because there's not going to be any quizzes like that. I'm usually just going to use quizzes just to make sure that you guys are participating and listening. But I don't expect you to remember that it's like obliquity and precession and eccentricity of the orbit that causes these cycles. The idea is to just understand that there is like a cycle. There's multiple cycles that occur over multiple years, multiple thousands of years, that can increase our chances of being in an ice age. So if we look back over here, we can see that you have 100,000 years going, and we go from interglacial to an ice age. So there's a reason why there's all this variability, and why that these peaks, these glacial periods, interglacial periods are pretty regular. And this is just it's like a theory. No one's really sure if it's true. Can it be argued that we are heading into another cycle now? That's a good question. Well, let's look. So we are here, we're in interglacial, and we've been there for about 10,000, 12,000 years. So if we think back to what the video was talking about, I think the smallest time scale where there is a difference in, I think it was precession, that was 26,000 years. So we're pretty firmly within the interglacial period. We're at like basically the beginning of the interglacial period. So we've got about 14,000 years to go before we hit a period where we might end up in a glacial period. So I would say that we're not quite there. Yeah, but I can look more into it and we can discuss it next time. Any other questions? Okay. So the reason I'm talking about Milankovitch cycles is because I want to just make sure that we understand what was happening in the Pleistocene. We have this change in climate that's happening, variable climate going from really warm periods to really cold periods, et cetera. And then we also have humans coming into these ecosystems and new species or wildlife being exposed to this new predator that's on the landscape. So we have basically a double whopper of climate changing and humans coming into the play. Um, so this is a tangent, and this is where this is where we get into one of the parts of this class that might be a little harder for you guys to accept, being raised basically in the idea of Western science, objectivity, rationality, measurements, etc. And it was pretty hard for me to accept too while I was making this lecture. But it's an interesting tangent, and I think it's worth looking at, because this class is looking at indigenous management styles, indigenous conservation, indigenous science. And indigenous science looks a lot different from what we raised in the Western tradition think of as science. So, mythology, Mesoamerican mythology. And this is the only paper I could find about it. It was on ResearchGate. It wasn't published, but it was pretty interesting either way. So did Mayans actually know about these Milankovitch cycles? And the reason I got interested in this was because I was learning about Milankovitch cycles for the first time as well about a couple weeks ago. And I remembered this whole idea of Mesoamerican mythology, and there are different ways of kind of collecting years, thousands of years into a discrete unit. So we have basically what's happening here is that we have ice age cycles. For example, if you guys remember in the video, I was talking about 41,000 years, and this is the time period where I think the angle of the earth changes. It can go from the north can go from 24 degrees towards the sun, or 22 degrees. This is where it changes, 41,000 years. This is 13 backtunes. And backtunes are just a measurement of years for Mesoamerican mythology, basically Mayans. And it's about 5,300 years. I might be off by a couple of decades, but they sort of collect 5,000 years into this thing called backtunes. And 13 backtunes are this, it's sort of like it's a bigger discrete unit. And I'm just going to move to the next slide. So one Mesoamerican myth is this idea of the five suns. And basically what's this means is that the world ended at least 4 times before humans, we humans, this generation of humans basically came onto the scene. And the first time the world ended, the sun went black and jaguars ate everyone. This was because the humans pissed off some gods or something. And then the second world ended in a global hurricane. The third world ended in drought and fire. And then the fourth world ended in a global flood. And then the fifth world should have ended in 2012. And if you guys remember all that mess about the Mayan calendar and the end of the world, that's where it's coming from. The 13 backtunes is what basically separates the fourth world ending and the fifth world ending. So all these time periods between the first world ending and the second world ending and the third world ending is 13 backtunes. And I just thought this was interesting because if you go back to, let me see. Yeah, if you go back and you count these discrete periods of years, you have a Mesoamerican civilization sort of starting at this period, a little bit after this period, after the world ended in a global flood. And at this period, you have this warm spike that happens. And we know that when global temperatures get warmer, you get a decrease in glaciers, glaciers melt, sea level rises, etc. So that can be thought of as a global flood. You go back the next 5,000 years, and you have the world ending in drought and fire. And this is the 8,200 year cold event. And this was basically within the Holocene. So this level period of warm temperatures right here is when the Holocene starts. In this cold period uh, happened about 8,000 years ago. So when global temperatures get colder, what tends to happen is that things get drier. There's less precipitation, there's more drought. Obviously, the sea levels decrease, and there's more land that people can use. But this idea of the third world Indian drought and fire, when this cold period happened, and supposedly it should have been less moist, is really interesting. And then you go back to the second world ending and the global hurricane. This happens in a sort of in like a warm peak, or when the warm temperatures are rising. So if you have increase in temperatures, you have more moisture in the air. And at this period where you're actually going from cold to hot, you can think of that as of right now. So we know that when the climate is getting warmer, and if you increase the temperatures, and um, things are going to be more variable. There's going to be more extreme events happening more often, and so that includes hurricanes. And then you have this period over here, the late glacial maximum, which is when it was really, really super cold and really dry. I think it was like the coldest period, one of the coldest periods in the last 20,000 years. And then you have the first world ending when the sun went black. And then jaguars ate everyone as well. So that's interesting. But I just found that these different discrete periods, sort of these different endings of the world, sort of matching up with these different climate changes that happen across the globe. So these they're called Dansgaard Oeschger interstadial events, is when the climate sort of fluctuates, and this causes fluctuations in vegetation. And I've been talking about this before, but I'll just make it more concrete. When global temperatures get warmer, we see more moisture in the air, we see sea levels rise, and vegetation, like if it's grassland, it might turn into rainforest because um, there's more precipitation, there's a change in biome there. And then when it gets colder, you have drier air, you have sea level decrease, and you might go from forest to grassland. All right. First, let me see, does anybody have any questions? Okay. So during this period of the Upper Pleistocene, about 130, starting 130,000 years ago, you have all these species that are across the globe, different types of animals. Megafauna are the most popular, the more well-known species that are present in across the globe. Giant sloths, etc., mastodons, mammoths. And what I want you guys to focus on in this is just the idea that species extinctions, basically, over these different periods. So from late Pleistocene, 125,000 to 70,000 years ago, we have 13 species going extinct. And then we see 51 going extinct in the next 50,000 year chunk, and 150,000 happening, 157 species going extinct in the next 10,000 years after that. So there's definitely a change in biodiversity during this period that's happening. And the question is, why is this happening? So there are three different kind of groups of hypotheses that were that have been brought up to sort of explain these minor mass extinctions. The first one is the climate's changing, it's too variable. Vegetation is changing with the climate, so animals that are used to grassland are suddenly in forest, and they have to they have to migrate, and they're less healthy because they can't get the resources that they need. And then all of a sudden the climate changes again, and they got to go back to where they were before. So there's different shifts in range due to climate changing. um, is supposed to have sort of destabilize the megafauna populations and made them easier to go, sort of kind of drove them to extinction, this variability. Then you have overkill, which is basically putting the blame on these extinctions on humans. So this idea again of this new predator coming onto the scene and wildlife not knowing what to do or how to respond effectively, and humans just basically killing everything that they can see and wiping species out. And then you have all these other hypotheses. Uh, Disease spreading is one hypothesis. Uh, there's a great fire, which is really interesting. And then you also have this thing called the Dryas impact, younger Dryas impact, which is basically an asteroid hitting the Earth around 15,000 years ago, 13,000 years ago. And supposedly it wasn't like one of those it wasn't a dinosaur killing impact size impact, but it was big enough that it um, caused a lot of carnage in North America, and it threw up dust, and it caused the global temperatures to decrease for a bit. um, there's That's still not really proven, and it's kind of thought of as a crackpot theory, um, but it is one hypothesis that's out there. But basically, the idea that I'm trying to get you guys to think about is this: not that it's just humans, and not that it's just climate, but it's that it's climate and humans kind of causing this issue for megafauna. So here we have this graph from this paper. It's really complicated, but I'm just going to make sure that you guys know what I'm looking at. So if an animal is facing this way, like this rhino right here, it means it's going extinct. So this rhino goes extinct right at this period, about 29,000 years ago. So do mammoths. They go extinct around 29,000 years ago. But we have short-faced bears, which are these giant bears, bigger than polar bears. And they're actually supposed to be pretty vegetarian. So it's not like they were really chasing humans around. But this idea that they are supposed to be actually invading, so increasing their range at this period. But the idea behind this graph is that you have all this climate happening, all this climate change, all these different peaks and valleys and warm periods and cold periods happening. Um, and then you have all of this extinction that's happening, and you're not able to sort of match it up. You're not able to match up the increases in warm periods with an animal going extinct, a cold adapted animal going extinct. Um, and we see the same thing that's happening over here in the later lower Pleistocene, around 15,000 years ago. And this is all in Europe. You can see that this is the Irish giant elk. I'm probably saying that common name wrong, but it's that species of elk that is supposed to have these really, really big antlers. And they also went extinct about 10,000 years ago. And this is ah, this is when humans, Homo sapiens, the modern Homo sapiens, were supposed to go into Europe at this point, around 44,000 years ago. And then Homo sapiens were in the New World, so North America and South America at this point. So over here, we can see that Homo sapiens come up onto the scene and we have extinctions, but it's not like centered around it like this is right here. So there's obviously a whole bunch of factors happening. Um, if we're looking at overkill, the overkill hypotheses, there are some strains of evidence that are sort of support this idea. Um, so obviously, if you have a mammoth, um, big animals, you get more bang for your buck. If you get one and you kill one and you can bring it down, then you have food that can last you and your family for like a month or more. But the idea that people need to they're trying to figure out is the idea of whether we were megafaunal specialists or whether we were generalists. So were we all just focused on megafauna? We were more focused on getting that really big score that could last us for months and months, or were we people who were just walking around getting what we could? If we ran across a mammoth, we would go for it, but we were fine with going for rabbits and bird eggs and berries. And people still aren't sure. Um, so this is a graph from Africa. And Africa, sub-Saharan Africa, is one of the regions that had the least species extinctions back in this period of the Pleistocene. But we can see that as the years go on, and you're going to read the graph from right to left. It's flipped, unfortunately. But you do see that you have this decrease in size occurring right when humans sort of come onto the scene. You have this increase in smaller animals that happens. Body size 2 is like up to 80 kilograms or something like that, whereas size 3 is much bigger. And these are size 5 is the megafauna, so the big animals like mammoths, mastodons, etc. But you do see this dip in these animals that you would think is caused by humans hunting them. And there is evidence of like overkill sites. So these are a couple of them. This is where people found mammoth remains with arrowheads, and or the bones were cut. So it seems like it was likely that it was caused by humans. The death of the animals were caused by humans. But you also have to think about, so when I was mentioning megafaunal specialists and generalists, this idea of searching for food, and if you run across a megafauna, then you might go for it. You have to think about that because if these are big animals, right? So if they're on the landscape, they need a lot of resources, and the more resources they need, the less dense they're going to be because there's only so much land that can support one individual. And the less dense they are, the more time it takes to actually search for them. And then you also have to bring into the idea of actually killing them, which is not always guaranteed. So encounter rate and handling time. You have basically these animals. The more time you can sort of give to this hunting of these animals, of these finding of these animals, even though they're so rare on the landscape, the more likely that you are to put them into your diet. So this is a graph from Argentina, and Argentina, South America is where we had these giant sloths at first. Horses as well. Horses were actually native to North America and South America for a bit, and then they went extinct. And then Europeans brought them over again, so that's pretty cool. But we can see that there's not really a focus necessarily on megafauna. These are remains that are found in archaeological sites. So again, cut bones, arrowheads, etc. We're not seeing really like a really focus on megafauna. They're there, like there's remains, but it's not like we just went for them all the time. There's more smaller animals there. So obviously these graphs sort of show that we're kind of going for whatever we can get. We have more smaller bodied animals in our diet at this point in Argentina than giant sloths. Okay, I'm gonna stop and ask if there are any questions. Okay, so we are gonna continue on with this lecture. And we stopped right on the concept of island biogeography and metapopulations. This was a theory that came out in 1967 by thought up by MacArthur and E.O. Wilson, which is a name that I will talk about a little bit more during this class. Not now, but about 2 months into the future. So the idea of island biogeography was looking at what influences the species richness and diversity, and also the probability of colonizing a patch of area or going extinct from a patch of area in isolated patches of habitat. And the isolation, so how far a habitat patch is from a source or a mainland in this case, if we're thinking about where it came from, islands. So the isolation of an island from the mainland is important. The further away it is, the harder it is for species to colonize the area, and the easier it is for species to go extinct from the area and not be replaced by other individuals of that same species in the future. The size of the island is also important. So bigger islands hold more species, and they're also easier to colonize compared to smaller islands. And so when you think of islands, islands of habitats, this obviously translates very well into urban ecology and studying how animals are able to survive and thrive in isolated patches of habitat like parks or woodlands that are surrounded by neighborhoods or protected areas, for example. And just so this is clear, this is Central Park. So obviously, any animal that is intending to colonize Central Park is going to have a lot of trouble getting through all of this urbanization, the matrix, as they call it, so non-habitat. And some species are able to do this, some are not. And the more isolated this patch is, the more urbanization surrounds it, the harder obviously it is for a species to get there. So basically it's this idea of a population of populations, right? And this is just an example. We have 4 habitat patches in this case. And the circle around these habitat patches shows that even though it might be difficult, individuals from each patch can actually disperse into another patch. So the populations in all these patches are mixing, and that makes it a metapopulation. As long as there is some mixing, some dispersing between the patches, it's a metapopulation. This was an idea that came out in 1969, Richard Levin. But obviously you get into this issue of not all habitat patches being equal. So for example, even though this habitat patch is bigger and it should be able to hold more species, it might be that this habitat is just not a good quality habitat, and it's hard for animals to both exist there and to reproduce there. So it's actually called a sink in this case. Animals come from these patches, the green ones, and they basically get lost into this black hole of this habitat patch, this sink. Over here is a smaller habitat patch, and it's further from the rest of them. And the habitat quality is also bad, so we end up with another sink population. But if this habitat patch had really good habitat and the species that were there were able to reproduce and the individuals were able to disperse, it could also be a source population. So these right here would be source populations. The habitat is good enough that there's reproduction and there is a surplus of individuals that are actually able to disperse out into different areas. So why am I talking about island biogeography and metapopulations in this lecture? Well, it's so that we can sort of look at this idea of climate change and humans sort of working together to cause the megafaunal extinctions. And I'm just going to show this video really quickly. Okay. Pause it. Go. All right. So this guy obviously uploaded a lecture on the megafaunal extinctions, and he'll sort of go into a little bit better than I could how climate change and how humans and this whole idea of metapopulations might have driven the megafauna species to extinction.
Now, I want to run through the climate change here just to show you that it really was a tough time for animals. And down here at the bottom is the 15,000 calendar years ago, and we're moving up towards more recent times at the top. It's a warm period. It's the beginning of a warm period, then the warmth ends and it gets cool, and then the cool ends and it gets warm again, then it gets cold, then it gets warm again, and then it gets really cold for 1,000 years. Now, you might think this probably had something to do with the extinctions, but the point is the extinctions occur apparently before this, sometime before this for many of those taxa. So, and it also is all before this, before the real cold, is when the Clovis people are around. So this is the interval here of major importance between the cold and the warm period. But things are happening in here that's probably not good for any animal. The rapid oscillations, even though they're taking 1,000 years maybe, it's still hard on animals to readapt because the vegetation takes a while. It lags behind when climate changes like this. And here's an even more boring graph, but it also shows you much more clearly what's happening. When the lines are up here, the blue and the red lines are up here, and they're measuring things from ice cores, it's warm. When the lines are down here, it's really cold. So things are going back and forth, cold, warm, warm, cold, and then it gets cold for a while, and then it goes back to warm. And then you've got this real cold period that starts and lasts for almost 1,000 years here, the Younger Dryas, as it's called, which is named after a Scandinavian flower. So here's the time when people show up in North America, and here's also the time the extinctions occur. It's not the cold that does it. And you may have heard about the recent theory that a comet blew up over Hudson Bay 13,000 years ago and wiped out all those animals, which isn't really standing up to much scrutiny anymore, but it has been advanced that maybe that's what happened that caused the Younger Dryas. A comet blew up, but I'm not even going to talk about that because that's sort of another 6-hour lecture. Okay, so where do I start trying to figure out what's the best explanation? And of course, there's a couple of ways to do this. One of them is just to look at the fossil record as it's been collected in a database called FaunMap. Just look at all the little dots on the maps here of where these particular animals that are now extinct have been found, dating to around 13,000 years ago. So here are little dots for Columbian mammoths. Here's the Jeffersonian mammoths here. the one-hump camel here and the horse, one kind of horse here. Look at where they are on the map and then try to figure out, does this tell us something about extinctions that are going to occur right after this time period? And apologies for how densely technical and boring this part is, but if you draw a line around all those dots, it would look like this. But you can't assume the animals are uniformly distributed inside that line around all the dots. So what I've done here is try to figure out, there are places where there are more animals than outside these things I called sources. So you've got the sinks where animals don't really spend much time, and populations are there, but they're not reproducing and they're not increasing in size, and sometimes they may not even be staying steady. But you also have these places which are good for those megafaunal, the 35 genera, to be. So those would be the sources and the sinks, and then there's migration routes between them. So it's kind of patchy. And this is what North America must have been like 13,000 years ago in light of all those climate changes that are occurring, the 1,000-year reversals all the time. And this is what you see today. I mean, if you factor out human interference in ecosystems, this is what you see. There are better places to find some animals than other places. Those would be the sources. So keep in mind that each source, and here's a different model of how extinction may have occurred that I think is misunderstanding that. If this is the whole continent and you have high density of all those taxa, which is what the darker shade means, as it gets lighter, the animals are beginning to disappear. It's sort of assuming they're everywhere in the same density, and then they start going down everywhere in the same density. So it's hard to imagine Clovis people, 9,000 Clovis points, killing enough to make this turn into this low density number of those mammoths or mastodons or anything else. So a better model would probably be one that takes into consideration that last slide I showed you here. You've got sources with lots of animals in them, not a lot of animals anywhere outside the sources, not uniformly distributed like over here. And each one of those is going through its own sort of loss of animals due to climate stress and maybe human hunting. So they're disappearing like this, which has a couple of implications. First off, the whole continent is not, and I say that again, is not teeming with big animals just before extinction, or any time probably. It's not like the Serengeti. You see pictures of this all the time, and somebody says this is what the Ice Age was like, where there's animals like that, and you picture them everywhere like that, every single place in North America. It's not like that. There may have been animals like that in these sources, but not out here. So the population, you have to sort of wrap your head around this. The population of all those animals that became extinct is probably much smaller than you might be assuming. So it's much smaller because there are places without them, and it's much smaller because each one of them is getting some stress from environment and human hunting. Now this is maybe the worst slide up here, so if you're trying to figure this out, there's two things on this slide to remember. I tried to estimate how many mammoths and mastodons there could have been at 13,000 years ago based on the fawn map that I showed you earlier. So we got 80 sites of mammoths that date to this period, 13,000 years ago, and there's 174 individual mammoths in the 80 sites. And then mastodon, you got 105 with 145 individuals, and horse, there's this many, and camel, that many. So you got that many sites, and you draw a line around it, and it's that big a part of the continent. So you look at the nearest living relative, the horse, the elephants, how many of them sort of average out per square kilometer or square mile today. How would it look if you had that many square miles or square kilometers, the maximum number available for the whole area based on where these sites are and the line you draw around them is just this many mammoths and just this many mastodons and this many horses. So these are numbers that might be huge levels below what many people assume was present in all of North America. And that's just based on an average density per square unit of land. There's another way to do it too, which is to look at the number of live and dead that you see in modern animal communities today. Biologists use this number, the live-dead ratio, for studying trees or anything else. You count the number of live animals in an area, and you count the number of dead ones, carcasses and skeletons. So it's usually a small proportion of the live population is also dead at the same time, like 1% or 1/10%. So if you use those numbers, like 1/10% for elephants, and that's what it is in elephant range, in healthy elephant range, 1/10% of the total number of live animals can be found as skeletons. And then you multiply that by the number that has been recorded by paleontologists, you come up with a much smaller estimate for each one of these different taxa here than just using the average range. So whatever the number is, it's pretty small. And if you add these together, all 4 of these, there's only this many for all of North America. Now, obviously, this is really hardly supportable. I mean, this is just reaching, grasping at some way of estimating numbers where you don't have much data. We don't have all the sites that we know of. We don't have any way of estimating population density, because these are extinct animals. We don't know how they behave. But this is what I've tried to do twice now, and I've come up with low numbers in each method. So keep that in the back of your mind. There's not a lot of big animals at 13,000 years ago, apparently. So,
Okay. So I'm not sure what he was talking about with the ratio of live dead. I've never heard of that. But I mean, I've only been in this field for a few years, so I can't really say that I know everything that's happening. So any questions? No? Okay. So, summary, we have megafauna that are going extinct during this period of time, about 20,000 years that they're going extinct during. And we're looking at humans and climate change most likely being the factors, the causes of these extinctions. But what is the impact of these extinctions? Because think about it, if you have elephants taken out of the ecosystem in a certain region of Africa, then you are obviously going to have impacts on the vegetation, on the other animals that are present there, on the environment. An animal the size of an elephant makes a lot of impact on its environment. And you can think of them as keystone species. They have a very high impact for their biomass. And so just as an example, I'm going to use elephants again as an example, but if you take elephants out of a savanna, for example, you will end up with shrubby trees growing back and an increase in biomass. And this is because the elephants actually, they'll browse on the trees and keep them sort of short, and they'll keep the seedlings from growing. And they sort of reduce the load of shrubby mass that's in the environment. So if you take elephants out of the savanna, you might end up with woodland, right? And that's kind of what happened. That's kind of what scientists believe happened when the megafauna went extinct. So you have this increase in woody, shrubby environment instead of this grassy sort of open ecosystem. This was a habitat type that actually occurred in Eurasia. It was called the mammoth steppe. And it's believed that it was mostly just grassland because of the mammoths and their browsing. So with this increase in woody, shrubby habitat, you get an increase in fire, which has a huge impact on the environment as well. With this increase in biomass, you have a loss of these open ecosystems. And then if you think about species that have co-evolved with these megafauna, because they have been around for thousands and hundreds of thousands of years by now. If you think about species that sort of co-evolved with these megafauna, for example, oh dear, hopefully you guys will see that. For example, we have avocados, and it's believed that they co-evolved with giant sloths. And this is because their seed, the pit, is so big that a modern day animal can't really swallow it, digest it, and sort of disperse it as we believe that is supposed to be dispersed. And Finally, with all these changes in ecosystem structure, with this increase in fire, and with this loss of a species, multiple species, you have cascading effects that we can't even really trace yet. So the loss of these megafauna had a huge impact on ecosystems across the globe. So moving into Holocene, which is about 11,000 years ago to 2,000 years ago, humans are everywhere across the globe, except for Antarctica. Madagascar, it's still under debate, but it seems that scientists, researchers tend to think that humans colonized Madagascar around 2,000, 3,000 years ago. Again, it's still under debate. And with climate change, we have this sort of warm period that we're still in. So we have these warm temperatures, it's pretty high up, and it's relatively stable. There have been a couple of cold points. We have the 8.2 Ka event and the 4.2 Ka event. But other than that, it's been basically stable and warm. And that's not to say that there hasn't been periods of great environmental change. I'm going to share this other video with you guys.
People think of classical dancers as like these perfect, soft fairy tale characters.
Researchers have also managed to get radiocarbon dates from organic-rich sediments and artifacts like baskets, which show that human populations throughout the Sahara peaked between 9,000 and 5,000 years ago. And on top of the archaeological evidence, there are even little hints of the African human period within some cultures of Africa today. For example, languages from Mali in Western Africa and Ethiopia and Eastern Africa are now very different from each other, but they still have similar words for hippo. Some linguists think this could mean that people from these cultures once lived in the same place, among hippos. Of course, the Sahara returned to a sandy desert at some point. The rock artist kept painting, and their later art showed that new animals arrived as lakes and rivers began to dry up, and the ecosystem shifted from savanna to desert. And paleoclimatologists have used the same ocean sediment cores that revealed the start of the Green Sahara to figure out when it ended. Dust records show that there was a dramatic decrease in moisture around 5,500 years ago, and that the humid period only took a few centuries to end. When Earth's orbit shifted once more, the incoming solar energy decreased, and the northern hemisphere cooled down. This pushed the monsoons south again, closer to where they are now. And sure enough, the archaeological record shows that people who lived in the Sahara abandoned their northern sites first, and then the other sites farther south. All in all, the African humid period ended quickly, at least in geological terms. And when it did, people clustered back around the Nile and other water sources, while the Sahara became more like the environment we know today. So, thanks to a
So we can see again that that video mentioned this idea of the Earth's orbit shifting and that causing climatic change across the globe. Okay, so I'm just going to talk about the regions and how they changed and megafauna populations changed during this upper Pleistocene period. In sub-Saharan Africa, we have humans, behaviorally modern humans arising around 125,000 years ago. We do have climate changes, mostly in the guise of shifting monsoons, like that video mentioned, and then also decreases or increases in precipitation. But this does have an effect on the habitats. So if you have more precipitation, you will have more forest, more rainforest, more woodland versus more drier habitats like grasslands. Now, researchers have found that 3 species of megafauna have gone extinct in sub-Saharan Africa, but this is likely an underestimate. It's because there hasn't been much research on megafauna, and species extinctions in the past in sub-Saharan Africa. And this is probably because of that whole idea of, well, these species sort of evolved, co-evolved with humans in all their forms. So of course there won't be as many extinctions in this region compared to others. So if you assume that there aren't as many extinctions in this region, you aren't going to put money towards looking for extinctions in that region, if you understand what I'm saying. In Eurasia, we have humans, Homo neanderthalis, around 300,000 years ago, and then the behaviorally modern Homo sapiens, 44,000 years ago, possibly Homo erectus, 1.9 million years ago. Climate has also changed. We get to a warm period around 14,000 years ago, and it's estimated that 26.5% of the megafauna species been extinct, including the Neanderthals. But this occurred in 4 extinction waves beginning in 130,000 years ago. So it's harder to sort of correlate the extinctions to the presence of humans in the environment. On the left, you can see just a figure from Stewart 2015, and it's just a figure of all the species that have gone extinct or are still present or were still present during the Holocene. So we have mastodons, mammoths, and short-faced bears, which were vegetarians. We have spotted hyenas, and then we have Neanderthals. In North America, we have modern, behaviorally modern humans coming in by 13,000 years ago. We have climate changes, again, vast ice sheets covering most of North America, and then in 16,000 years ago, you get rapid change in vegetation because of changes in climate, and this sort of continued on until about 8,000 years ago. And it's estimated that 69% of species went extinct during this period. In South America, again, behaviorally modern humans, 13,000 years ago. Now, climate changes in South America are a little bit different because it's not so far south and not so far north that you'll get extensive ice sheets like North America, but it is assumed that, you know, the changes in precipitation, like with Africa, cause the expansion and reduction of open habitats. It's assumed, or it's estimated that 80% of megafauna genre went extinct. And there's a lot of questions about why so many species went extinct in South America, but didn't go extinct in Africa. And some people have suggested that this is because most of the South American megafauna that we know went extinct kind of come from Southern South America, which is closer to Antarctica and is more likely to be glaciated. So it's possible that there needs to be more research done on this to actually get the true numbers of megafauna that went extinct. In Australasia, so this is the region of Tasmania, Australia, and New Guinea, people are still not sure about when behaviorally modern humans came into the picture. Estimates range from 62,000 to 43,000 years ago, and this is a very fierce debate because it's sort of, if humans came too late, then they can't be the cause of a lot of these extinctions, because these extinctions happened pretty far back in history. Climate changes, again, it's more of a precipitation factor than it is whether there was ice sheets or not. And then it's estimated that 80% of species went extinct during this point in time, but there are problems with radio dating and the taxonomy of species, so there still needs to be more research. And again, there's that fierce debate of whether it's humans that were a big cause or whether it was changes in the environment that were a cause. And yeah, finally we have Southern Asia, which In this case, humans, we know that Homo erectus was there 1.66 million years ago, and then we have behaviorally modern Homo sapiens about 40,000 years ago. Changes in climate induced changes in precipitation and also changes in sea level. So during the glacial periods, you would have sea levels drop and more lands and more islands were connected to each other through land bridges versus interglacial periods and warmer periods where the sea levels rose and those islands were once again isolated. And it's estimated that 20 or more megafauna species went extinct during this period, but again, there is more research needed. So the takeaway for this lecture is basically that it's assumed that the pre-exposure to human lineages might explain why Africa and Eurasia and Southern Asia had fewer extinctions, but there still needs to be more research done. And it's this assumption that causes the lack of research. And it's sort of like, it's like a feedback loop almost. Basically, most archaeologists and zooarchaeologists assume that it's human hunting and rapid climate fluctuations and environmental fluctuations and changes that caused the megafaunal extinctions. And this is in comparison to the ecologists who tend to assume that it's mostly humans that were the cause, the overkill hypothesis, this idea of humans coming into a new environment and just slaughtering everything they see. And finally, we come to the last point and probably the most important with the megafauna extinctions and this loss of multiple species that had huge impacts on their ecosystem, having serious cascading effects on ecosystems, even up to today.